Um, I'm Pieter van Schalkwyk. I'm CEO at XMPro, and I'm also the chair of the Natural Resources Working Group at DTC, which is really the focus of today. So I've got one or two slides just because people ask me, so who's XMPro? We're an Australian-based software business that focus in the industrial space, specifically mining, oil and gas, asset-intensive industries, with mostly on things like digital twins. So Gartner brought out this Technology Innovators report in September, and they included us. Proud to say the only Australian company on this list, but that's the focus. And in terms of who we work with in the mining sector, we work with mines directly, but also with some of the OEMs. So this is one of the OEMs who, if you look at the front end of the services and things that they provide, the traditional historians like Aviva, OSI, Soft, and other products at the back, but on the front end in terms of creating the digital twins there. But that's enough about XMPro. This is about digital twins, and the first question is, so what is a digital twin? There are probably 254 different definitions if you Google it. So at the Digital Twin Consortium, we thought we'd add one more. Took us 6 months to get to this line, which says it's a virtual representation of real-world entities and processes that are synchronized at a certain frequency and fidelity. And that's the kind of the key word is, yeah, we all understand it's a virtual or digital kind of thing, and it is about assets and processes, like supply chains potentially. But the real caveat is that it is synchronized at a certain frequency and fidelity. If it's not synchronized, it's just a model. And then there's some better or defining the why, how, and the what in terms of it. So just some clarification that the digital twins are there to help with understanding, decision making, and taking action. It's based on data in the past, present, and more and more around what we can predict in the future. But it is motivated by outcomes. So it is driven around a specific outcome and tailored to use cases. We'll touch on use cases a number of times. Powered by integration, built on data, and it needs domain experts to create these, and quite often we implement them in OT/IT systems. So this is the Digital Twin Consortium definition. The gray model base that you see there is something that I've added. It is implied in terms of how the DTC describe it, but I just made it more explicit that it is a model-based approach. If I put that into a picture, you've got the physical thing on the left-hand side of the screen, and then the digital version on the right hand, and we've got data at a certain twinning rate. That's when the synchronization happens. For some instances, it might be millisecond. For others, it might be minute, hour, day, month. There's no rule around what the synchronization or the twinning rate should be. But in order to get a twin, I need to take the physical and make the digital. And sometimes the digital can actually inform or make changes into the physical. So it's not necessary, but it could happen that way. So very simple diagram, and we'll also get back to this one a little bit later. Sometimes get asked, so what's the difference between a model, a simulation model or something like that versus a digital twin? Well, if you look at the digital twin prototype, which is really the descriptor of what this, it could be a drawing, it could be a data sheet, it could be something that defines. This is normally a standard template. So looking at a digital thread, we've got these use cases that go across the life cycle, and we initially said there's all these use cases that we have. A digital thread is what we build as we work through these use cases. So the digital thread is almost like the digital breadcrumbs, and the digital twins are the use cases that sit across this. The biggest value that we see from digital twins is that we can now make implicit intellectual property explicit. So we've got all this institutional knowledge of people working there and the processes that they do, all the intelligence, the data, all the metadata that we have. And now we have a structure which has got models, taxonomies, integration, again, AI models, and some UX in the front end. And combining all of this is now giving you some new enterprise intellectual property that can help you make better decisions, create an integrated enterprise view, and help with improved processes for recommendations. This enables us to deliver new digital products and services potentially, but also operationalize our enterprise strategy. So if we have and we can also make this composable at scale. Operationalizing that strategy is, let's say, for example, that we want to run more often or produce more when running. What levers do we have? And that's one of the advantages of where we're moving to with intelligent digital twins, which I'll share in a minute. But digital twins is really a framework that unlocks the business value when you want to do this at scale, because it makes it explainable, because it's model-based. It makes it useful because it's now digitized and accessible. And it's also scalable in the way that it is all model-based and then instantiated across a large number of things. So why do we then need to move to intelligent digital twins? We've just now figured out what is a digital twin. What we're seeing is that how decisions are made have changed. We've seen a massive interest in AI and how that could potentially be deployed, and then also organizations are now thinking about, how do I scale this out? It's one thing if I do it for a small unit. How do I do this at scale? And that's where intelligent digital twins are coming in. So one of the biggest things that we see is that decision making is changing, and some people are talking around we creating decision intelligence systems that are supported by digital twins, and there's external information and internal things. And historically, it was all about dashboards, BI, so I could go and analyze what happened in the past. I would do some condition monitoring. And we're seeing more and more decision augmentation at the moment, where we're starting to use AI, and so that can help me get better. The co-pilots, front-running simulations, closed-loop feedback. And what we're starting to see is an area of decision automation, because we don't have enough skills, we don't have enough engineers. How can we create a safe operating envelope where inside that I can allow the digital twins to automatically make decisions and run operations? And this is the current shift, and this is the shift that we're seeing as organizations are starting to embrace this part. Now, a lot of people will say to me, well, that's really in the domain of control systems and automation systems. And what we've done is, because people understand in mining, oil and gas, and these asset-intensive industries, the concepts of DCSs and SCADA systems and the Purdue model of 5 levels. If I take that and that's really my control part, if I flip that over and I say, well, what does it look if this was a digital twin-based approach? And could I, in an organization, have both? So where I have the controllers sitting over here in the normal automation pyramid that we're familiar with, those are the digital twin use cases in the digital twin world. I can then create that same supervisory digital twins, again, looking as I'm starting to aggregate it. And I can create a layer for business process logic and models and an AI that will allow me to create a operations tower where I now have levers. So if at a strategic level, and we can create even a higher level at the top, which is a common operating picture, and that will allow me to change rules that will influence how the digital twins will make sure that we execute the lower level. Let's say, for example, I need to maximize throughput right now because oil prices are at an all-time high, or I need to reduce that and improve cost reduction levers. This gives you that ability to do that. So this is the framework for more intelligent digital twins, and looking at how can they work together and not just isolated, but they're still made up of use cases. So there are use cases that drive all of this. So it's not this mega uber big digital twin. They focused around value stream focused use cases. And quite often we see this as an ecosystem of vendors. It's not even a single vendor that can provide this whole thing. You need to put this all together. And the way that we've described it is kind of in a value stream at the top. So I can see the mining value stream, and you can expand or contract this based on kind of your operations. And these are 8 areas that we've seen appear in many, many different digital twin use cases across multiple industries. So they apply to manufacturing, to healthcare, to energy, to a whole bunch of different ones, and as well as mining. So around process optimization, quality, asset performance, massive one. ESG, a lot of focus on what do we do in that. Safety, that's a critical element. Workforce management, and more supply chains as well. And then building out, these are the different use cases, and all the X's are the ones that are very unique in your business that you would map out. But this is the landscape of digital twins. The trick is to choose which ones to start with, and that's a separate presentation and webinar. But what this portrays is that digital twins is not a single thing or a big mega uber twin. It is actually a bunch of applications across the whole value stream across those areas that share a common approach around how to create models and how to extract intelligence from that. The next part is we're seeing more and more intelligence. So it's not about better technology, it's just smarter digital twins. I mentioned Dr. Michael Greaves, who was kind of the father of starting this movement in 2002. I had the opportunity to have lunch with him at one of our DTC meetings. And in 2022, which is literally 20 years later after he initially introduced the concept, he also introduced this concept of intelligent digital twins, which is going from, we had the drawings, started making models. We then said, okay, let's make some ad hoc. Let's create a twin here and a twin there, but not really on a platform. The next phase was creating platforms, and this is really where we're seeing a lot of effort right now. And then going forward, this notion of intelligent digital twins that supports things like front-running simulations. And so what is, and I'm just going to put all of this on here. So if I compare the two, the traditional digital twin was really about data, where the intelligent ones are more around data flow and what can we do with data flow. So the first one is more like metadata, storing it all, passive repositories, where the intelligent one is more of an active, almost agent-based. So it's almost like the digital twin is running next to the physical one and informing the physical one of potential things that could happen. The traditional digital twin is also offline. Even if you take something like airbags in a car, it waits for something to happen and then it will actuate. The online or intelligent one is running right next to it and in real time and scanning, and it can actuate based on what is potentially going to happen. Just imagine if you had airbags that could expand before an accident, not as a result of. Traditional digital twins are quite often goal given. We're trying to optimize this, we're trying to optimize that. It's not goal seeking. And again, a whole area of study around how do we make them more goal seeking with its own intelligence. And predictive, yeah, they can predict things, but they're not anticipatory and don't really support what is called front running simulations. So this is kind of the difference between where over the last 20 years digital twins have come from and where they're heading from. That front running simulation, best example is Formula One. Got all the telemetry, all the information from the track. And these guys are collecting 100,000 data points per second at 200 miles an hour, fastest moving edge device out there. And there's a digital twin around when for fuel and all of these different things. That's a front running simulation. A better example is when you actually combine the Formula One car with the track information. And in this instance, 1.1 million telemetry points. But what they do with this is really a whole bunch of front-running simulations and use cases. So they've got a lot of use cases around race strategy, competitor analysis, car performance. So you can do pit strategy, pit windows, predicted stop strategies, driver performance, all of these, because you can spin up time. you can run it faster than real time, which is really what a front-running simulation is. I can take data now and spin it up and come up with. Now, one of the interesting ones is undercut thread. So this is actually where I monitor my competitors, tire wear and all that, and I'm trying to predict at what lap they're going to come in so that I can strategically work out what is the best time for me to come into the pit. All of this, a lot of AI and things done with it. These guys spend tens of millions and sometimes even hundreds of millions of dollars on this. Just imagine if you can do that for your mine, but not at that price point. And really, that's really the focus that we're trying to get to and work that we're trying to do with intelligent digital twins. So the traditional one, passive, offline, goal given, and where we're heading is having this almost agent base. The digital twin have this separate capability that runs next to it. That's based on expert knowledge, rules, math, stuff that we do right now, getting into more AI, and you'll see as the colors get darker, more advanced AI as we go forward. This is all great. And the question I get a lot is, okay, so how do we do this? How do we build this? So we came up with a framework, which we call the Intelligent Digital Twin Framework, which says, in order to build these things, architecture, I need to think about that they need to be integrated, they need to be intelligent, they need to be interactive, and I want to make it composable so I can make it reusable and even provide a marketplace for some of these capabilities. I asked Midjourney to give me some pictures around what each of those mean, some AI, so that's it. But if you break it down to be integrated, it's standards-based APIs, model-driven development, again, coming back to models, bi-directional, because now the twin needs to inform the physical. Making it intelligent, we want to make the AI not just an engine, we want to plug it into the business process. Quite often we see a lot of these engines out there, but how do I use it? So making it executable is a key part of bringing intelligence into the twin. How can I apply it for innovation? How can I also provide augmented AI, things like co-pilots that will help and provide that level of intelligence that I'm expecting? And then I need to make it interactive so that we can collaborate and have a kind of a basis for whatever the industrial metaverse is going to look like in future. We don't know. And also support things like operate by wire, because we can fly by wire, drive by wire. I think we can also operate by wire in a certain safe operating envelope. And lastly, we want to make it composable so that we can reuse this in many different ways. So one of the ways that we apply it is we start with, we've got all these assets and we can collect data for the integration part through what we call our data stream designer. We may or may not plug that into the AI part. We want to provide the visualization so the intelligence could be in the data streams, or it could be in AI. I want to provide some user experience, and then the real value is when this digital twin can provide recommendations, recommended actions that we can help people, processes, and automation to get those outcomes that we showed. So connecting this, the first part, the data streams, so integrating all these different data sources that we have, from historians to sensors to all of this. If you're using standards-based APIs coming from here, and this is a model-driven approach, so this applies to one pump, but it applies to 1,000 pumps. So I don't have to build multiples of this. I can use a model-based approach to do this, to build my digital twin data ingestion part. I can also embed AI into this logic, and I can also provide bidirectional and make it bidirectional, push it back. The intelligence part, in this instance, we've embedded something like Jupyter Notebooks into the digital twin as well, so I can start building AI models, use a lot of the existing model libraries, repositories, things like that. And then getting to the interactive part, there's the nice visualizations and graphics, and this is a wear pump with some real-time data, some predictive models about remaining useful life. But I can also use a co-pilot capability. So again, this is an intelligent digital twin that provides me a lot of new intelligence that I wouldn't have had. But quite often I still want what was in my OT system. So what's my ERP system? So what maintenance do we have? It's great to have all of this, but I also want to know what the current work orders are, what's the maintenance history, what's coming, what are the real-time sensor data for this to make the best informed decision. And that's what a intelligent digital twin delivers. And then part of the interaction part is also providing recommendations. So how can I provide a recommendation with, this happened and there might be some triage instructions and, some analytics around how often this happens and, again, informing it with AI and intelligence. The last part of that framework is to make it scale, so make it composable. And this is based on kind of composable business applications, which is a kind of architectural concept. We've put in the things from from the engineering environment as the main elements or data elements to bring into these capabilities or package capabilities, as Gartner and other organizations call them. So how can I bundle some of these things together and make it reusable, and then just compose my digital twins so that I can create these use cases like conveyor maintenance, centrifugal pumps, first pass yield, coal wash plant throughput losses, or energy monitoring for CO2. And again, this is areas that we have built tooling around, but the whole concept of composable is, think about this formula, this racing car. If I can take the blocks apart, I can build a 4x4 by reusing most of the parts. I may need a couple of others, and then I will also have a few spares left, but I can build a completely different thing by recomposing the blocks that are here. And that's one of the things that, from a digital twin, to make it scale, there's so much capability that if we model it and package it right, that we can do this. And it's not just the twin, but also the environment that it works in, that it lives in, is part of that. So now going back to our drawing, we came up in the Digital Twin Consortium, we came up with what we call the capabilities periodic table, which has got 6 main areas. The one is around data services, integration, intelligence, UX. So how do we manage all of this from an IT perspective, and then the whole security and trustworthy. So the capabilities periodic table is a framework, especially if you've got multidisciplinary teams that need to agree on what the requirements are when it's a complex system. That's always hard when you start that part out. So we try to make it simpler by looking at how can we think about capabilities and compose that, rather than getting into, well, is this a technology A or a technology B, or should it be a sensor A or sensor B? So the 6 areas that we have are those that I described, and for each of them, there are a number of elements that sit down. I'm not going to. This is all available on the DTC website. I'll show you the link in a minute. 62 elements. So when you're thinking about a digital twin, what capabilities do I need for my use case? Not all use cases use all of them. Not everyone needs batch processing or AI or gaming engine visualization, but most of them need security, safety, resilience, reliability. So using an example of a wind farm, these are for just doing condition monitoring. These are the capabilities that I would need. And then later I can figure out what technology would support that. Do I already have it? But if I want to do energy prediction, now suddenly I need things like machine learning and AI as capabilities of this digital twin. It might be that I don't have them. Are we going to hire, recruit, partner? What is it that we're going to do to acquire those capabilities as well? But this is, it is supported by a spreadsheet that you can fill in for each use case. And if you've got multiple use cases, you can then define for your business what are the digital twin capabilities. It's almost like when I hire a digital twin to come and do a job, what is on the resume or CV? What are the skills that I need? And then I can get into technology. Then I can get into who's the technology provider. So there is a user guide on how to use this. And on the Digital Twin Consortium website, under initiatives, you'll see, and this is downloadable for free from there. I'm going to finish off just with a couple of examples, very briefly, of some of these intelligent digital twins. So this is underground mining operation, 1.2 kilometers underground, 80 kilometers of underground conveyor, and trying to reduce downtime due to fluid couplings. And this was at the start of the project. This is the visualization in this instance is like a London tube map view of these. This is my conveyor system. The intelligence sits in the calculations and the recommendations. And these are engineering calculations, by the way. They're not AI calculations. So this is amps across motors and things like that that help us identify. And within 5 months, this is the result of applying something like this, where the digital twin, again, the visual representation is a two-dimensional London tube map style view of the solution. The benefit of making it composable is we could do this in 30 days. And if you look at the volume and scale, about 42 million messages a day across multiple use cases now. Which includes about 340 million data signals per day. So that frequency and fidelity definitely there. The biggest benefit is actually not just having that single use case. Again, if you look at that overall value stream map, it's when we start adding, we could do the conveyors, the borers, the pumps, crushers, fans, and then also some OEE. But starting out just with a specific use case and then building out that use case, so adding more capabilities to that use case and reusing some of it in different places. Even putting things like computer vision on the belt to look for splice problems and things like that. So we're building the conveyor digital twin over time. We're not starting with this massive, uber big digital twin, building it over time. And then combining the conveyor, the hoist, and the borers, for example, to create an underground twin. And again, this is an approach where it's more composable, and it's focused around capabilities, as I've shown. So sometimes the graphics, again, the higher up you go, the simpler it needs to be. For a GM of a mine, this is put to port around, what is happening. And again, same. When there's an issue, a recommendation so the recommendation is not just at machine level, but you can also provide, how do we provide a consistent way? How can the digital twin advise us in a consistent way across multiple managerial levels, shifts, things like that, in a consistent way of doing things? This is an example of looking at operational information as well as issues from a potential operational issues coming from a maintenance perspective. Doesn't just include kind of tails and cyanides and things like that, but also there's a potential issue with the crushers. And intelligent digital twin in this instance, this organization's got 6 primary crushers, can run at full production when 5 of them are running. If you have a 4th one going out, then you need to throttle back production, which again is a huge impact for them in terms of revenue. The objective of this digital twin, intelligent twin, is to predict the liner wear, and then based on that, when the red areas that you see are when two crushers are potentially out at the same time. So the machine learning model that sits at the back is about the liner wear, and it's not about trying to extend the life. It's just making sure that we don't have 2 crushers out at the same time. Getting down to the crusher level, you can see information around, the vertical travel is the proxy for the wear, and then not that it was that important, but you can see the tons per liner. But also, again, what work orders do I have? What is the maintenance schedule? And does this overlap with some of the others? And then lastly, the visualizations could be anything from GIS information. So I can see all my haul trucks, and then drill down into the haul truck, looking at again, getting recommendations from the, lost my mouse, getting recommendations from the system on where they are. And again, this is a nice 3D model that explodes, providing real-time additional metadata around the application. Recommendations on what to do when this happens. And then lastly, looking at where we're heading with mining 5.0 when it moves beyond fully automation, but how do we, again, make it work with people? This is smart mining set at the center, and there's all these things around it, smart products, smart factory style approach. We want to make it secure, trustworthy, responsible, and this is all underpinned or held together with intelligent digital twins. So that's me. Can now open the floor for questions.